Yeah, welcome back to Cloud Computing and Big Data. Today we have our second part of Lecture 2, Machine Learning Models in Clouds. And in the first part, we were having a little bit of moderate introduction to machine learning. So for sure, that was not a proper, deep, detailed introduction to machine learning models, but at least it gives most of you that have not been in touch with machine learning before a sort of basic understanding required to really go ahead now and using these models in cloud computing. Also today, when we have now our second part here, in the clouds, we will start very moderate. We use something like Google Collaboratory, which is in one respect a very simple cloud compared to the ones we use in our assignments later with MS Azure and then big Spark clusters. We have here a small Spark instance we use, but it captures already the essence of remote computing, of the packages required, the software required that have to be somewhere in the clouds, and we will make a case for it. We also will reuse a Jupyter environment of sort. It's integrated in this interesting Google Colab environment, which we will explore today. So hence, the basic idea is not that you become directly super experts in machine learning here, and also not how you become super experts in cloud, but how to try to now merge these different disciplines and also thinking about real applications, because that's why we also want to think about machine learning in this course of cloud computing and big data. Of course, machine learning is the idea of learning from data, and in this course also big data, and we will make the case in different application scenarios throughout the course. But again, as I promised at the beginning of the course, we will start very moderate so that everybody can follow, even those that don't have a big machine learning experience and also that don't know much about cloud computing. So when we motivate this a little bit, so thinking about, again, our 3 steps, why machine learning is, a good idea. We want to have a pattern. And here's an interesting application example, a food inspection in Chicago in the restaurants, right? Those that have been in the States, it's quite interesting to see that sometimes you have their banners saying A, B, C quality restaurants. And when I was with my lady in New York, we found that quite exciting to go to a D restaurant type or quality measure. So it's an interesting situation there, but of course, very interesting to that as Europeans. And this food inspection is taken very seriously. So the application example we put here is something which is really happening. And you want to see different violations of the restaurant. So if you think about giving quality measures, is it, let's say, will it pass or fail, making it a binary classification problem? We want to have some features looked at, and this might be the quality violation. So we are basically getting data from the city of Chicago. So we have the, let's say, third element as well. The data exists. There's a data collection from Chicago, and of course this data is available. But I just want to make it as a nice example again that, of course, there's not really a mathematical formula yet of saying, well, this particular restaurant on this particular street has to fail, and this particular restaurant on the other street downtown has always pass. So this is something where, of course, this screams for machine learning. So we have lots of text data. We can look at the quality violations over time and then form our idea and, let's say, our prediction that this particular one will pass or fail. In addition to this, it's not only the quality violations, it's another set of, basically a supervised setting. So we have, of course, the data available for those that already passed or failed as a guiding label, if you remember the supervised learning, what we had in the last lectures. Hence, this would be an interesting idea, and in the CRISP-DM model analogy, we would call it the business understanding here, right? But let us have also other examples. So this is a famous example, and when we then would go ahead now to think about how we would use this in a bigger cloud computing setup, we need some sort of idea that, okay, you can imagine this from all restaurants all over Chicago, this might be a lot of data. So maybe your, let's say, laptop setup with Jupyter Anaconda and Serial Scikit-learn would be not good enough, right? And then this might be not only that the memory maybe is not, enough, it might be also that the laptop is just too slow to perform the machine learning or the optimization that is inherent in the machine learning approach. Hence, you would go to the cloud computing. So that would be your step. You would have to have a subscription. We will talk about this also a little bit more on the assignment and then throughout the course, but usually would have something like pay per use, pay as you go, as it is actually called in MS Azure. And this would give us then, let's say, a cloud platform called HD Insight, which is fueled with those interesting stacks we will have also in the next lecture, like Apache Spark, for instance. Hence, we had to focus here a little bit. So while we already learned a little bit about Apache Spark, the really proper introduction of Apache Spark is in the next lecture, because here we wanted to focus a little bit again on the cloud computing as such, using machine learning again. And with this also, let's say, formalize a bit machine learning again, right? With the different steps, putting it in context to CRISP-DM, how the data comes in. And we will come back to some of the terminologies we had really in the introduction. So training set, test set, why is that useful? We have something like features we will discuss. Features is a very important term for machine learning. To learn from data is not just throwing data to this machine learning algorithms. You have to craft features, you have to identify features, and we will talk about it. But coming back to the cloud computing approach, here we would usually go ahead then and deploy a Spark cluster and use HD Insight for it as an example. You can have also other machine learning solutions, like in AWS, you would say, well, the SageMaker, for instance. Then you have the Jupyter Notebook that, I mean, the majority of you know from the Python courses and so on. And then we use a so-called PySpark kernel with this open source tool, Apache Spark. And Apache Spark is loaded. It has support for SQL. It has support for machine learning with the MLlib. It actually has support for streaming and graphs and so on. So here we put the emphasis today on the machine learning library of Apache Spark, and we will also hear more about it in the next lecture. However, then we will continue. We create a Spark session remotely. Hence, this makes now the cloud computing approach, right? This is all remote. Hence, you also have to upload the data. We will see about this today when we think about a bank data set, for instance. And then you can start, according to the CRISP-DM model, a little bit the initial data analysis, the visualization of the data, understanding the data, and start then the modeling of your machine learning model. And then, of course, training it, optimizing it. We will make another important link today between machine learning on the one hand and optimization techniques on the other. And then you, of course, want to evaluate your machine learning model. Is it higher accuracy? Is it a, let's say, lower error rate? These are all different evaluations or error measures we will look at, like the F-score and so on. And then you would start off refining the model. You would perform maybe cross-validation and other parameter techniques, which then are also more elaborate, coming in lecture 13. So we learn here many different basics again to really go through all the course, put again an emphasis on the idea of using here a very simple application problem, but still captures the essence of machine learning at large as well. You also will see here again that many of these different Jupyter notebooks, if you are basically at some of the lectures or some in the environments already have access, have a specific kernel even for PySpark, which we also will reveal a little bit here and in the assignment 1, of course, as well. So coming to the real use case I wanted to convey today, right? Yet another application examples, but this is the one we want to know in detail. So we go step by step through our approaches to understand this little machine learning exercise here. And little is loaded because, again, many of the techniques that work for the little problems here will also work for the big problems, right? Because the cloud is scalable. We can then extend. And here with the bank clients term deposit, the application name is basically inherent in this. You want to find a pattern. What of the bank clients would actually say yes to a term deposit or no? So again, we have the, let's say, one of the most simplest forms of classification, binary classification, essentially saying yes and no here. So, and we believe there's a pattern, right? We have certain age classes, we have certain other properties of persons, and for instance, also their occupation, their jobs. You see here musicians and so on. And other people maybe that have a certain pattern if they do, spending for the bank or not. We have also data, luckily. So that's a third ingredient. There's data actually from Kaggle, and this allows me also to give you another interesting data set collection. Hugging Face is yet another, but we also heard about the UCI machine learning repository. So there are many open source data collections, which are already a little bit, let's say, massaged, prepared for machine learning problems to learn from. So once we have this data, we can also imagine now with a pattern, we don't really have a mathematical formula, right? So the second of saying, well, musicians always do bank deposits and managers never because they have to, finance their Porsche. This is not true. There is no mathematical formula that derives from all the features given a, let's say, very clear x in, which means our client, and then we get always the same y out, which would be a function. So this is basically not existing. Hence, we go here for machine learning. And this also shows now in the CRISP-DM guide the idea of the business understanding. We well formulated what we want from the data. We look at persons that we have in the database and what do they do a term deposit or not. So we have a good business understanding. We know there's some data. Now it comes to the cloud computing stepwise approach. Before I even start with more elements, I would say now to my boss, we have to invest in the cloud infrastructure, or if you want to have, let's say, little starters, as I promised you in the beginning lectures, we will start small. You can also do some decent job with a Google Colab environment, especially here, of course, for education. It's free of charge. The pro version costs a little bit. I already was alluding to this in previous lectures. So here we use a Colab idea, but then also we'll see in later lectures how easy it is now going from the Colab environment then actually to a real, let's say, cloud computing scalable solution, which is provided then by Amazon Azure, Amazon Web Services, or the Google Cloud Platform that, of course, offers similar things with Apache Spark, but then you have to pay, of course. So here you would go through the same steps, create a subscription, again, something for here in the Colab. It's free in the course because the Colab, it gives you essentially one GPU, or you do the pro version. It's a little bit of cost, but still a relatively low cost subscription. Then we will deploy a Spark cluster in this. So we will download it actually from open source as we do. And then basically we'll start a PySpark kernel and use it all over the analysis, because we want to use the PySpark with a machine learning library that is in Apache Spark and which has already certain algorithms implemented for the cloud, like logistic regression, for instance, that we want to use today. But there are many others. There's trees and so on, recommender engines and whatnot. But today we focus on logistic regression out of this platform. We will use this certain Spark sessions then to see how we can do this with our application data set. We will visualize the data a little bit, do plots, but also understanding how we then can form this machine learning model on the Spark cluster. Towards the end, then we will also see why model evaluation and refinement is important, how we justify it in the evaluation. And with this, we have a good chance of understanding how we can tackle, let's say, basic machine learning problems quite already by using the Google Colab after this lecture. So it's very similar also to the conceptual ideas we had in the beginning of the lecture. If you remember, yes, is this a flower of this type or that type? Here, we basically have just yes and no bank deposit or no bank deposit for a person, right? But if you look at the person, you will never know. You would have to look at much more features, right? Similar like we did with the flowers. So again, think about the first step was create a subscription, and we have now the Google Colab array. This is a simple step in this particular lecture because we start small. And of course, you need a Google account for that. And once you have done this, you can actually use a collaboratory with quite nice scripts, which are actually fueled inherently with a similar idea or almost same idea like Jupyter notebooks are, right? So this is really portability. We can use then these notebooks also in other cloud infrastructures. Of course, we have to always think about the versions. Hence, we come to the first really idea of how we now use that. And this is to create your environment. Now, this is something where, of course, different clouds have different solutions. So here we look at Google Colab. It's a very general tool. So there's no real pre-setup of Spark, of this open tool set we're going to use. Hence, we have to download this. And you see here, we even need one prerequisite, which is a Java environment, a JDK. So we basically install this. You see here with the command apt-get, which mimics a little bit the Unix commands, right? Every time you see this interesting character here, we basically leave the Jupyter environment and go to a sort of, command, which is the typical Unix command, for instance, like wget, get the HTTP package, right? So we start with this installation of Java in the first step here. We get the distribution from Spark that is basically now in a tar.gz file, so it's basically compressed. We wget it. That means we download it to our cloud environment, right? So this is now not on your laptop. As you execute this within the Jupyter notebook there in the Colab, As you execute this remotely, it will be, of course, downloaded there. As it shows also with this ls-l command. This is another Unix command for showing what is in my current directory. So also very important. When we want to work with this Spark environment and the Spark code, we of course have to untar it. So we basically have to get this, compressed archive uncompressed, which you see then here also when we look at the files. Now we have Spark available. As a prerequisite then of working with these environments properly, we have to set the Java home, the Spark home, also something which is now forming more or less our operating system, our OS environment, and prepares then for our next executions. Again, Apache Spark as such, and many of the details here and there, why it's open source and so on, will be something we also discuss a little bit in lecture 3. So using the Jupyter Notebook then further in step 3 means we have to create now this PySpark environment, right? So, and this is something what we want to understand. We want to see later different types of PySpark. Here we shortly have an SQL element and then a Spark session that is going to be created. But there's also different sessions in different packages. And for us now, very important is that the data, right, is, if you remember in the directory listing, not existing, right? So we want some data, but we don't have this. There's some sample data from other projects. But essentially, and you see them here is MNIST, character recognition, housing, and so on. There's no bank.csv. Hence, this needs to be manually uploaded in this environment. And this will be also later available for you, this kind of exercise when you do assignment 1. But this means for terms of data transfer, we also have to think about how in and out of computing clouds will be. And we will make another case for it, of course, when we go bolder to saying, what about transferring big data? How that should work and why basically this should be maybe already uploaded to the cloud environment with other possibilities instead of just drag and drop here, right? What we can easily do because we have the Jupyter Notebook as a UI here. You can imagine this will not work when you have very many gigabytes to transfer. However, once you have done this, you have the bank CSV now manually uploaded in the Jupyter network. It's a comma separated values file. Basically sort of representation of the data. When we now want to look at the data using a little bit more the idea of the cloud and Spark, we see here, for instance, one example of just how the CSV file of the bank is structured, right? So we want to basically see the schema, right? So what information is there about a person? And this is one thing, right? Again, think about the person's analogy here. We have here age, we have a job, we have the marital status, what type of education, etc., balance, housing, loan, etc. So interesting enough for us as a supervised learning problem, we have also this interesting variable here, deposit, right? Which makes it not just a feature or a variable. Some would say even it's an output variable because this is the things we maybe get into the machine learning, but the deposit is now something that is a label. Right? For unseen data, that is what we want to find out. Do they do deposit, yes or no? So basically, that's why it's a yes and no variable. So some of you have heard maybe about pandas. Now, usually in the course, I ask who knows pandas. Is another, let's say, more popular set of illustrating data sets these days. It's a bit prettier if you want, but in the end carries, of course, absolutely the same information. But here the advantage is we can inspect the data a little bit, right? So we see now, okay, the job is a sort of interesting variable, which is, has a string, and then the deposit is also not 0 or 1 or something like we had in the flowers, or basically in the earlier one on the perceptron with -1 and +1. Here we have yes and no, apparently. So we see a little bit what type of variables these are and how they are filled, right? So this is quite important for us to understand a little bit how I use this now with machine learning. Right. And in a way, the days and months somehow seem to be not really quite interesting for us. If you think it's generally May and generally the 5th of May, this information seems to be not so really fruitful, while the others give you much more information about the person. So we do something what we first would say, do summary statistics. So we are now getting to the CRISP-DM model in thinking about, we have a certain data understanding, right? So that's why I go back here. So we want to have the understanding of the data. in terms of summary statistic. That means, for instance, if you do classification, in this particular example, you have binary classification, 2 classes. And when you do this, you want a certain class balance, right? So it is important for us to keep the class balance. And you see here, we can do this by grouping them to the deposit, which was our important guided label, Y, right? So it's a no or yes. And we have almost a similar amount of count. So of course, they don't need to be exact the same, but the, let's say, order of magnitudes should fit to each other. So here it would be very bad if you would have, let's say, almost 10,000 no's and just 200 yes. This would be a classifier which would be biased towards one class, not good for machine learning. By having checked this, we can go to the next part and see a little bit again the minimum max value. So there are lots of elements in the data understanding that you can do. For time reasons, we go not in all of them now, but it shows you a little bit the idea of the data, the age ratios from 18 to 95, for instance. That's quite interesting. Okay, we have also youngsters in, they have maybe not much money to do a deposit, but yeah, then we have also very old people, maybe 95. We will see how that then comes, but it gives us a little bit of information. Also that the day, for instance, from 1 to 31, well, thank you very much. We know that already, right? So this is something where in some of the aspects you would say, okay, that gives us information. And now we go to the next step and would say, this is all good. We understand already from the data that maybe day and months are not so useful, so we sample them out. And this brings us in the CRISP-DM to the data preparation. So we modify the data a little bit. We prepare it for the machine learning steps. And this is a very common aspect. It's actually very loaded, could be feature generation, could be lots of different elements, what we also will discuss in a minute. So this is a very loaded topic, and we start here by feature out, basically remove from our features the day and month, and then print it out the schema again, and you see day and month is gone. Then what we actually using, and this is also something which is a bit bigger topic, of course, for Spark and why it's so useful. We have lots of helper tools, and one of them is to form, for instance, a very nice feature vector, which is a very compact, mathematical, convenient representation of all the data we have seen in one single feature. And we see that firstly in understanding what are the categorical columns that we then want to one-hot encode to make a very compact representation of them. So for each of them, we have a sort of different index if you want. Instead of using the text representation, this will be numbers, right? The index of these different jobs and the different marital statuses and the different education. They all have string values, as we were finding out by data understanding. However, not all of them have been strings. Hence, we have, of course, the idea later also to have age, balance, duration, and so on. These things which are more the, let's say, real values, to actually put them together with the numerical representation from the strings. And then we have also the kind of information we got also of the real numerical values. There's one, of course, that is very special for us. You see that here, and this is something we create new, right? So the deposit should be essentially a label that we know, what we learned already in the course. So that was for the flowers, -1, +1 in the perceptron learning algorithm and so on. So this is now also a string index that we form. So here we will have also compact representation now if the deposit will be yes or no. And we put that all together and have an interesting data set, which is now essentially features. You see at the output column here, features, and the output column label, augmenting our data set in a very mathematical, convenient way. It's just numbers. And then also very compact, right? Because we have one-hot encoding and just one feature to work with and giving us out the label. And this will be quite useful for many elements. So, and the data preparation in that sense is now exactly what I was talking about. Here's a code from PySpark, a little bit about the pipelining idea. We will talk in a minute, but you see here essentially the labels and the features that are now there in basically the data set, something new crafted, data preparation in terms of feature generation, if you want, of course, reusing the data, right, that is there before. Now, an interesting thing in industry usually is the idea of having complete pipelines of data analysis and Word is loaded. We have several transformers and estimators available in Spark, which we will talk also in lecture 3 more about it, just to make a certain case that many of the elements we want to do, if you put them in a pipeline, you can more easily repeat them, right? In a pipeline here, we put, for instance, the selected columns, label, and features alongside with the other columns. And then we basically select these selected columns and have a, a kind of pipeline that gives us later on also an interesting idea of how we firstly can transform it and then evaluate it, but also use the same pipeline for different elements. And here is something what I already alluding to. We have now these 2 interesting labels. If you want to take a couple of them, the data frame here, take 5 of them, just as an example. We have then this kind of columns. You see now how that looks like. We have a label which has now a numerical representation, not anymore like deposit, yes and no. And we have features which are now also for mathematical convenience, not anymore strings or anything that you see here, but also numbers. Having done this is data preparation, creating new features. We have to do one of the most important decisions when you come towards the modeling. Hence, in the CRISP-DM now, we have prepared the data. We move a bit to modeling. And modeling entails learning from data with a specific model. And learning from data means, okay, our prepared data. But now the big question arises that I was alluding to earlier. What is a training set and what is a test set? Right, again, you have just a limited number of training examples that you have to choose. It's a quite of interesting approach. Many would say 70-30 is a good rule of thumb, but it really depends on the number of data you have. And even some people would say, let's take a couple of validation data sets away from this training samples. They're neither training set nor test sets. They're just used for model selection in something we called validation techniques. So this is alluding to lots of machine learning theory of bias in the data. When you, for instance, use the same data for training and tests, this would be unwise, right? Then you have not unseen data that you should have. Hence, the idea is here to work on the training data, give it to the algorithm, learn from it, optimize it, and then the testing data set we throw in the corner. We don't touch it. Once everything is trained, once we have our model to perfection, so to speak, what we think in our training set, we take the testing set again and test it really if it is good enough. So it's really the last check at the end where we should use a test set. And you see that nicely represented here. We have a random split, 70 to 30%. The seed is sort of a little bit, let's say, artificial addition to it for reproducibility, so that we can check a little bit in the assignment that is based on this later for you, but also for people that want to certainly sometimes want to demonstrate a specific case, is something that gives you really the same, let's say, setup every time when you set the seed. So in other words, the randomly split is not anymore completely random. But this is something what you can, let's say, ignore a little bit. It's just a certain education case here that is something. And you see now how that is actually materializing in the training data set is having now 7,800 and then 3,300. But still, the mix from the ones that deposit and not deposit is very wildly randomly split, right? So we have no idea how many are in this and how many of that. But as we have given the same sort of 50-50 idea of deposits in the overall data set, this would be probably very representative also in the training data set and then later in the testing data set. Now, this was the first ingredient to the machine learning element. So what are now basically the training sets? The second ingredient is what compute algorithm you want to do. And we said before, we want to test logistic regression. We will talk about this more in a couple of lecture slides ahead. But let's take that now to understand one case, logistic regression. Okay, we have this features we just generated, right? This features column here that goes into it. And then we have a guiding label Y, which is our label, deposit, 1, etc. And then we have a certain iteration. We will learn now very soon that logistic regression is an iterative algorithm, almost similar to you have seen with a perceptron algorithm, right? To come to numerical values all the time. And this is what we put then in a so-called logistic regression function. The logistic function I was alluding to in the lecture already, the first part where I said we squash everything between 0 and 1. And here you see the most computing part the logistic regression model now, once you put fit on the train set, right, that you created here, and this now is an important part, you just use a training set to really create this logistic regression model. And that's usually where the computing starts a lot, where the iterative algorithm is starting to work, optimizing it with certain different techniques. Could be, for instance, stochastic regression, stochastic gradient descent. There are different optimizers, but we'll talk about it also throughout this course. But this is now where the computing happens. And when you have the Jupyter Notebook, usually this will take time, right, before you can then continue. Once you have done this step and we can say, okay, this interesting LR, this model has been now created, this LR model, it has so-called coefficients. We call that in the regression here, where we then see that are the, so to speak, the W's we really learned. And we can actually visualize these coefficients here, what was learned. And basically, this is something important for us. But before we go more deeper, we should also understand a bit about logistic regression. Again, it's always useful to go deeper with a machine learning course. And you can start with what we learned before, right? With the linear regression or linear classification, where we took the sign of W transpose X, or the dot product if you want, to have a certain hypothesis. What we done there was nothing else of computing a value, right? And by updating the weights all the time, this where we always knew values. And for each of the different sample in the data set, we took the sign. And was it the right class or not? Now, regression stands for real output. That's why we didn't call it here linear classification in the sense, or a logistic regression or linear regression, where you have the identity function in linear regression. But in the logistic regression, you use a so-called logistic function that you see here, right? So it squashes everything basically also in a sort of probability set here, and you have here the logistic regression function. However, we also need a measurement. So that is now good enough. And there's a so-called pointwise error measure that we have to go through to really check if we are on the right track, if the error is in performance from this specific weight we just updated all the time with an update rule. So we take basically go through the kind of, data set we have, and we have this guiding label Y here, right, in this pointwise error measure. That helps us that we can compute here everything and can see if the error in sample is actually then, going down over time. And this is something what we then so-called transform to a optimization problem. We call either maximization or minimization, but of course in machine learning, we often want to use it to minimize the error measure that we have here. And in this case, it's the pointwise error measure, and we'll use that. And the optimization to do that in a stepwise sense is something called stochastic gradient descent. So this is something where you take the gradient of a certain, point in time, and you would probably initialize the model. You see a little bit the algorithm here. You would have the weights that we want to train, right? The X is a constant, weights is what we learn. So we basically have to set them to some specific time, 0 to some values. But then we iteratively go over it. We compute the gradient of this in-sample error that we just have seen on the other slide, right? And take it as a specific point in time in this step. And basically have then also the gradient here, where we can then see in which direction we want to go. And of course, we go to minimize the error. You have this gradient, right? If you just take the derivative, you have the ascending part. But if you take the minus GT here that you see, but the gradient, that's the minus gradient, right? And this is the direction then going downwards. In other words, here, the negative gradient. So, and with this, we update the weights. So we say, okay, we have done this. We took the gradient. We understand now the value. There's a certain parameter here, the learning rate, which is a hyperparameter or parameter of this learning algorithm, really, to steer how quick we learn, right? So it's also an important factor. It should be not too big, not too small, an interesting factor. But it's one of the modeling decisions humans have to do. Or when we come later to AutoML, that can be also automated. So, and we do this many times. We iterate to the next step, and we will go downhill, reaching hopefully a global minima, not getting stuck in minimum errors. And this is what this algorithm entails. Of course, a visualization might help you as well. And as I said, there could be a whole lecture basically on the stochastic gradient descent. But you see here quite nicely in the graphic how we basically go downhill the error slope, if you want. And then by this, the loss or the error measure gets really downwards, downwards, downwards. And you basically have then also the performance here a little bit shown of the, you know, the kind of signal we're putting through the measure. So in other words, we have basically this learning steps. We have come to the solution of W that at some point in time will just stop. Of course, when the error surface would be much more wiggly, much more hills, the chances are that we get stuck in a local minima instead of a global minima, and this will harm maybe the perfect learning. But these are more, let's say, exercises for real deep machine learning courses, so we cannot talk about stochastic gradient over the whole lecture. We want to understand it a little bit more. And one of the next steps, of course, once done the modeling and have done this algorithm iteratively, is to understand its performance. Evaluation in terms of not speed in computing, but accuracy rates and so forth. And also here for the evaluation, it is really a domain-specific element. There could be an evaluation like you see here, the area under the RAC curve, for instance, right? And when you do this yourself in the assignment, you can play around a little bit with it, where you have then false positive rates and true positive rates. You see that a little bit explained here. Then you basically have the chance to understand that the area under the RAC curve, the bigger it is, the better the performance is the model. So, and this is something where, of course, maybe we have done some parameters which are not really the best, so we can maybe change these parameters later. There are other performance criteria like recall and precision, for instance. And you see that a little bit that these are already basically inherent when we have this training summaries, which is quite nice also to have, especially after this modeling, so that in the training summary, you can see a few things, how basically the evaluation was. And we seem to be quite good here because the training set under the area is 0.88%. So, I mean, 88%, so 0.88. So this is already a quite nice achievement in a way. But of course, machine learning would be never 100% so easily. And if so, it would be probably also biased or having lots of other issues. But also told you is now what we want to do is to think about more that we use a test set, right? And this is something what, you know, in the evaluation is quite important to think about now when we move from the thing that we trained to something we have never seen before, right? The test data is very similar, of course. You see here predictions from the LR model, the transform, the test set will have still age, job, label, and so on, and all of these. Of course, now they're part of the, you know, idea to put it also in the feature, right? So our pipeline idea that we had before. So then we basically transform it again and use it then also with essentially the kind of logistic regression model you would have here. As an evaluator, you can, you know, basically do again the test area under the RAC curve and see then with the predictions of this, you know, here you see the predictions select, essentially exactly on the test set, then how that well it performs. So we basically just use a prediction. This is nothing anymore like we had before, right? But this is now using the test set, and it also confirms we basically have an 88% or 0.88 under the RAC curve. It's not here in graphical manners. You know, it would be the same Python code, not really add to understanding, right? So this is an important factor. And towards the end of the course today, just I want to highlight a few things which would be then in lecture 13 relevant, for instance. All what we have done here is we use logistic regression in a very specific setup. It is, you know, has some predefined variables, really. The iterations we have seen, like 10 was also something where people say, maybe if we would have more iterations, like 20, 30, we might be better. We have certain regularization parameters, and regularization is an important part in machine learning theory alongside validation, really, which is here and there a good, let's say, regularizer in terms of how we can be performing better out of sample, right? And this is a generalization helper, this regularization. So don't take any signal by, hard, but think about a little bit of a regularization idea there. It's a topic where I would encourage you to really go to a machine learning course again if you want to learn more, or look one of my other lectures in this regime. And then we want to have this as a grid to now optimize across all of these different elements I can configure. Hence, we do something called a grid search, right, for cross-validation. So we will have a better understanding of this in lecture 13, right? When we think about parameter optimization, is very important in these modeling here, in logistic regression, very simple modeling, but it is of massive importance in deep learning in very large models we see in lecture 6 and 7 and later, right? So even here, it's already important, but you can imagine when you have bigger models and much more parameters like the number of neurons in a network, et cetera, this will be equivalently also very important. And there are systematic ways of doing it. Cross-validation is one of them here, where you see we give now this different grid here inside it and specify a 5-fold cross-validation. It's a certain technique really to do then another model selection, and then usually the prediction that you do on this model that you here again fit, right? So we again have the training set be fitted on this cross-validation technique with 5 folds. So with the basically still with the logistic regression, then we basically get a maybe much more accuracy, which is correct. And then, of course, what you want to do on the predictions, once you do this, the predictions, you get them for the test set, obviously, and usually end up with a model that is much more generalizing, with a perfect, or let's say a better way of having the right parameters, not the perfect maybe, but a better way. And then having less bias in the data. So you basically, you kind of report much more accuracy values or error measures that are, to the point, or basically, as you see here, the area under the ROC curve. Right, so this was quite a very compact walkthrough of a machine learning approach, fueled a little bit already by Spark and cloud technologies. Obviously, there are many other areas where you can do this. One of it is Amazon SageMaker, which also will come later in the course, but I encourage you maybe have a short video here on this. I will not do this as a video here. You can see and look on this on YouTube. We will continue then in lecture 3 to learn more about Apache Spark. Basically, we'll see a bit more in HD Insight and how we really use MS Azure then actually for our problems there. And that is also then the time next week when we're also starting then with assignment 1. So I hope that was quite useful as a quite of moderate introduction to machine learning on the one hand, and then also a preparation for getting more deep into cloud computing. Thank you very much and see you next time.